Hello, friends. Regarding geosynthetics, you have seen how it can improve the load carrying capacity of a foundation soil. So, various geosynthetics you have seen geotextile, geogrid, these are planar reinforcing material. And when it is reinforced into the ground, it is going to enhance the load carrying capacity of the foundation by many times. And in my last video, you have seen in the design problems how you can enhance it, how the tension that gets developed in the reinforcing material can be calculated. Also, the pull-out force that gets developed in the reinforcement can also be calculated. So it is pertinent to note here that what is the mechanism of interaction between the soil and the reinforcing material. What is the interface friction? How these reinforcing element interacts with the surrounding soil. How the traction force from the soil gets transferred to the reinforcing material. So all those things we will understand today in soil reinforcement interface friction. So this is very important. Soil reinforcement interface friction. Yes. So between soil and reinforcement, the reinforcement is going to be, let's say, planar reinforcement. So it could be geotextile. The geosynthetic product, it could be geogrid. Another geosynthetic product. And let's say this is the footing resting over the soil surface. So here, let's say this is the ground, GL, and the intensity of loading from this footing this is the intensity of loading, and you have the reinforcing element. So here in the soil mass, you have the reinforcing element. These are the reinforcing element. So in the ground, let's say there is going to be loose sand, loose sandy bed. So these reinforcement how does it interact with the soil? What is the interface friction? here what is going to happen? As you have seen that this is going to bend like this. So here your reinforcement is going to bend like this. It is going to bend like this. Going to bend like this. As a result, if it is a my reinforcement, the soil has the tendency to move like this in this zone. So they under the given intensity of the loading is going to move like this. As a result, what will happen? It is going to be the loose sandy ground, the pull-out force will come into picture because you are pressing it down in the loose sandy bed, there will be pull-out force. So the mechanism is, it is going to be a pull-out force will get developed. So here the pull-out force, the mechanism is as such that here, what is the magnitude of the pull-out force? That you need to find it out. So that is the soil reinforcement interface friction if it is loose sandy bed. But if it is dense, so let's say I have a footing here. This footing is now resting over dense sand. So this is the footing and the reinforcement can be shown over here. Let's say these are the reinforcing element as shown in this figure. Another reinforcing element like this. These are the planar reinforcing element. And let's say there is going to be dense sandy bed. Then, under the given intensity of the loading, how it is going to behave? You see here that there is a kind of shear zones, and therefore here the soil mass how it will interact with this reinforcing element, that is the moot question. So friends, if it is dense and dense bed, then the friction, interface friction is going to be like this. The soil is going to move like this. The movement of the soil is going to be like this. this, like this. And it will result into sliding resistance. So here it is being pulled out. Here, because of the frictional force that is getting developed because the particles are trying to slide. So it is a case of sliding resistance. So the mechanism is different in dense bed compared to the loose bed. How the particles are going to move? Here the particles are going to move in the downward direction, resulting into a development of the pull-out force. Whereas here the particles are moving like this. The arrow shows the direction of movement over the surface of this reinforcing elements. So these are the reinforcement over which it is going to move like this. And therefore, the sliding resistance will get developed. So the mechanism is going to be different. So therefore, from the soil, the traction force is going to be transferred to these reinforcing element. So to the reinforcement, it is being transferred. It is being transferred. But at one place it is sliding, at another place it is pull out. Therefore, if you want to find out the coefficient of soil reinforcement interface friction, so what is important is determination of soil reinforcement interface friction. How it get transferred. So at one place you find it pull out. Another place you find it is going to be sliding resistance. So if it is sliding, the particles, soil particles are sliding over the reinforcement, resulting into the friction. What you should do to find out the coefficient of soil reinforcement interface friction. So what is important is determination of coefficient of soil reinforcement friction. So if the behavior is like this, as shown in figure 2, and this is figure 1, two distinct behavior. If it is sliding resistance, how will you find out? How will you determine the coefficient of soil reinforcement interface friction? So here we perform to determine the sliding resistance. We perform modified Box shear test. Modified box shear test is just like your direct box shear test. How do you perform it? It's quite simple. You have a shear box, which is divided into two halves. Now, the lower half is filled with wood. And what you can do is you can fix here the reinforcing element which you are going to use it. So just here you fix up the reinforcing element. This is the reinforcement, geosynthetic. And you can fix it here. Fix it here. So it is completely in position. And the top is going to be filled with same soil. Whatever soil you have here, the same soil. Same density. Whatever density you have, say at the same density you can manage it. And then you can apply the normal pressure, normal force can be applied. And then you can move it and shear it. You can move it and shear it. So if you move it and shear it, what you are going to get? You already know the magnitude of this sigma n, the normal force, normal stress. The vertical normal stress is known to you, and you can find out what is the development when it is trying to move. There will be development of shear, that will be tau value, shear stress. So it is moving like this, shear stress in this at the interface of the reinforcement and soil will get developed. This value is tau. So now if you take a graph paper and if you have sigma n and if you plot this tau by performing modified box shear test, the sliding test, you will be getting a straight line like this. Let's say the unit weight is gamma 1. So you get this inclination is going to give you delta 1, which is called the coefficient of soil reinforcement interface friction. Now let's say the density is increased. So it is a function of density. Now, what is the unit weight? Unit weight is gamma 2. Then, for the given reinforcing element, you can find out the coefficient of soil reinforcement interface friction or angle of wall friction. mu equal to tan delta. So you can find it out by performing this. Mu equal to tan delta. So you can find out the coefficient of soil reinforcement interface friction. It is very popular modified box shear test and very simple one. It is similar to akin to box shear test. And you can use the geosynthetic and find it out. But the case is this. Then you will have to find out the pull-out force. Now here, what is the displacement? Where is the maximum displacement of the soil? The maximum displacement of the soil is going to be where? What would be the displacement of the soil in modified box shear test? Now, the maximum movement is on the top. So this is called the displacement of soil. During shearing, how the soil is getting displaced. Now, let us see when it is a pull-out force. How will you do it? Which experiment? So, in pull-out, the setup is quite simple. You can have a setup like this. There is a hole. There is the reinforcing element. And this reinforcement element is to be pulled out. These are the soil. Soil at a particular density. So, in a container, what you are having is the soil and this is the reinforcement. This is under certain pressure. Now, what is the pressure here? Let's say this is the depth Z. What is the pressure? What is the vertical pressure here? The vertical pressure is, if the unit weight is gamma, it is gamma Z plus, what is the surcharge here? Let's say the surcharge is Q at the ground level. So friends, you can very well imagine that the pull-out force you will have to apply here. Just pull it under the given intensity of the normal force or normal stresses. So the pull-out force is akin to this. You are trying to simulate the condition over here. And therefore, the displacement of the soil is going to be minimum here at the top and maximum here. So, let's see the displacement part. This is the point. This shows soil displacement. So, soil displacement in pull-out. Test. This pull-out force is also applicable in RE walls. It is a patented term. What is RE walls? Reinforced earth wall. RE walls are called reinforced earth walls. Very popular nowadays. It is a flexible walls, and under dynamic condition in seismic zone, these walls have performed very well compared to reinforced concrete wall. So RE walls have got its own advantages. How do you construct it? It's quite simple. You are going to have a facial element which is not subjected to any force, and you have a pad here. This is the ground. This is the backfill. And here you are going to place the reinforcement. These are the reinforcing elements. These are the reinforcing elements. This is called RE walls. In RE walls, friends, wherever you have a weak ground, you want to spread the load. Here, it's simply a pad, because these are the thin panels, facial panel, which are quite thin. As a result, you need a pad, not a heavy foundation. And you can have this kind of RE walls. These are the reinforcement. And here is the backfill. Side. These are the reinforcing elements. This is going to constitute a RE wall. And the failure plane with the horizontal, the slip line, is at an angle of 45 plus phi by 2, where phi is the angle of internal resistance. So, due to the movement of this wall, pull out, this is reinforcement. This is called resisting zone. Resisting zone. These reinforcing elements, it is try to move away from this. this slight movement will induce a pull-out force. So pull-out force is equally applicable for reinforced earth wall or RE walls. It is also equally important for embankment, RE walls, and also for embankment reinforcement. Embankment, reinforcement in embankment, soil embankment. Friends, we have now the tests available, whether it is a modified box shear test or pull-out test, will finally give you the coefficient of soil reinforcement interface friction. And as you increase the shear, we can see. I hope this is quite clear to all of you. I have explained it in detail. The whole concept is well understood. So, the displacement versus T, the pull-out force. Displacement delta L versus this pull-out force T is depending upon what? Depends upon what? It depends upon the unit weight of the soil mass in which it is reinforced, and also the surface characteristic. So this T is the function of this pull-out force. Is the function of unit weight, dry unit weight, gamma D, and the surface characteristic. Of the geosynthetic reinforcing elements. More rough will give you more pull-out force. If you are going to have rougher characteristic of the surface, if you are going to have a different texture, that will also give you this. So when the movement of the soil is going to be there, here you can just see these geosynthetic reinforcing elements have got longitudinal and transverse ribs. So longitudinal and transverse ribs. So this transverse ribs, this is called transverse ribs of geogrid. This is called longitudinal. Ribs. Now the particle is trying to move. What will happen? These transverse ribs are going to play an important role. So it will increase the pull-out force, transverse reefs, because the friction which is getting developed between the soil and these longitudinal elements also contribute to the pull-out force. But more important is the transverse reefs that will enhance the pull-out force manifold. So you have to understand in totality the behavior, the characteristic of the reinforcing elements. But if it is a geotextile, a planar material geotextile, the particle is going to move like this. There is no transverse reefs. So because of this, the particle will hit this transverse reef. It will hit it and it will be prevented from moving. It will be prevented from moving, leading into higher pull-out resistance. So friends, what is the surface characteristic? What is the kind of reinforcing element, type of reinforcing element? That is also important. Type of reinforcing elements. Geotextile or geogrid is very important. And if you want to find out the coefficient of friction, here you have found out delta value very easily by plotting here sigma n normal and you have also found out the value of tau and then delta as I have shown you. But here the pull-out, how will you calculate it? Let us see it. Let us see the pull-out. So, the coefficient of apparent friction in pull-out test, coefficient of apparent friction, not the mean friction, apparent friction, Fs star, will be quantified as maximum pull-out force. Maximum pull-out force divided by 2 into normal force, 2 times the normal force on the reinforcement. So this is going to be equal to the maximum pull-out force T max into 2. The normal force will be the vertical stress multiplied by the length of the geosynthetic reinforcement into BR. The width of, let's say, the reinforcing element, it has got the width is going to be BR and length is going to be L. And this is BR. This is the BR. Width and length. So you can find out this coefficient of apparent friction from this particular expression. So today I was able to explain the interface friction, soil reinforcement, and this is very important for all of you. Thank you very much.